Welcome back to my channel. This is part 4 of our Introduction to Calculus series, and today we're exploring limits. Everything you've learned so far brings us to this first real step into calculus. Let's get started. Consider the following function. Calculate the value for x equal 2. The solution is 3, right? Now let's calculate for x equal 1. What is the result of 0 divided by 0? Let's call the answer x. Basically, we're looking for a number that, when multiplied by 0, gives 0. But that could be any number. That's why we say the result is indeterminate. There's no single answer. Now, instead dividing 0 by 0, let's try dividing some number by 0. In this case, we are finding a number that, when multiplied by 0, gives y. But, as we have seen, 0 times any number is always 0. It's impossible. Or, in other words, it's undefined. Back to our function. Instead of considering x equal 1, let's approach it closer and closer to 1. Calculate to 0.9. Add more decimals. You can see it's getting closer to 2. Make the same thing with values greater than 1. Again, the same thing. It's also getting closer to 2. That's why we can say that the limit of f as x approaches 1 is 2. Let's plot this function. As you can see, it passes through 2 when x is 1. But be careful, there is a hole in this coordinate, because the result is indeterminate as we have seen before. This means limits are used to calculate the value of these holes. Yes, but not always. See the limit when x is approaching 2. The result is 3, which isn't a hole, it belongs to the graphic. So, we can say the first approach to calculate a limit is replace the value of that limit and see if it works. We call this method substitution. And what about the hole? How do we get this value? We should use another method. Try factoring the numerator. This is a difference of squares, which is easily factored as the product of the sum and difference of two numbers. The difference can be cancelled out by the denominator, leaving this simple expression. Now, replace it by 1, and we get the result, our whole. Consider this function. What happens when x keeps getting bigger and bigger? We saw this kind of behavior in the previous video. When x goes on forever, we say it goes to infinity. In this situation, we want to find the limit of the function as x gets closer to infinity. And what is the result? Let's calculate it, using each number bigger than the other. We can see it's approaching 0. Therefore, we can say that the limit is 0. Now, try calculating with smaller and smaller numbers. We want to find the limit when x approaches 0. Here, the result is getting bigger as x gets smaller. Therefore, the limit is infinity. If you plot this function, you'll see that the graph gets closer to 0 as x grows bigger, but never reaching it. You will also see that it grows forever as x gets closer to 0. What about this function? What happens when x goes to infinity? It's easy. The result is infinite. Now, look at this limit. The result also gets bigger and bigger. Correct? However, be careful about the sign. It goes to infinity in the opposite direction. Let's join these functions. What should we conclude about its limit when x goes to infinity? It goes to the plus or the minus direction. If you look at the calculations, you can see that function f grows faster than g. This is because it has the highest exponent. Thus, hx goes to the plus infinity. You can also check that by factoring out x squared. The limit of a product is the product of the limits of each factor. X cancels with the square. When you apply the limit, you get the inverse of infinity, which, as you saw earlier, approaches 0. Since the limit of the first factor is infinity, and multiplying infinity by a number still gives infinity, this confirms the result of hx. Keeping with the polynomials, let's see what happens when we divide one polynomial by the other. Let's consider these two polynomials and calculate the limit of their division when x goes to infinity. They have the same degree, 2. So, we can factor both by x squared. The x squared cancel out, leaving with this expression. Applying the limit, we know that the inverse of infinity is 0. So, the result is minus 3/2, that is, minus 1.5. You can also see it in the graphic of this function. It gets closer to minus 1.5 as x grows, but it never gets there. Here's our first rule. If you divide two polynomials with the same degree, the limit as x increases is the division of the biggest degree coefficients. We can now look at the two other cases. In the first, the polynomial q has higher degree than p. This means that q grows faster than p. That is, the limit is 0. Our second rule. In the next example, we have the inverse. P has higher degree than q. The limit is infinity, as expected, because p grows faster than q. Our last rule. But be careful. The highest coefficient in both polynomials is negative, which gives a positive sign. You can also factor it, simplify, treat the inverse of infinity as 0, and see the positive sign when x goes to infinity. And that concludes our lesson on limits. If you've learned something new today, make sure to like the video and subscribe. In the next lesson, we'll take our first look at derivatives, the mathematics of change. I'll see you in the next video.